Hi, everyone. We are going to start talking about continuous random variables. So up until this point, we've really focused on discrete random variables, but now we're going to start shifting gears after our midterm. But before I dive into a continuous random variable, let's just remind ourselves about the difference between continuous and differentiable. For continuous, we could have a function that might have kinks in it. In general, a continuous function, like when you're looking at a plot, is a function that you can draw without lifting up your pencil. But it could have these kinks like we have here, where the function changes its behavior at these particular points. In contrast, this function over here, it remains smooth throughout the whole time, throughout the whole function. This function is also continuous, but is also differentiable, meaning the derivative exists at all places on the function. So it actually meets both of these properties. In contrast, this function is not differentiable because it has these kinks. That's when we don't get that continuous derivative at every point on the function. But it is continuous. So now that we have that definition, we are ready for our continuous random variable. Oops. So we say a random variable is continuous if the CDF is differentiable. So just as a little reminder, I'll put a little note on the side, our CDF is the function f of x, which is equal to the probability that x is less than or equal to some little x. I'll make this little x so it's a bit more clear. So if this function here, f of x, is differentiable, so it looks smooth like this function, throughout all values in the support, then we say the random variable is continuous. That might sound a little bit weird that our restriction is actually that it's differentiable and we say continuous, but it is how the terminology goes. Now, you might ask yourself, what if I have something else? So this over here is our version of a continuous CDF. They generally, or a version of a continuous CDF. They generally look like this. They're nice and smooth all the way through. Remember, CDFs are always between 0 and 1. So the maximum it could be is 1 and the minimum it could be is 0. Over here is a version of a discrete CDF. We have seen these before. Again, the max is at 1, the minimum is at 0, and discrete CDFs generally look like a stepwise function. You could also have something like this one in the middle. This one is a mix or a mixture variable, a mixture random variable. It generally looks like a continuous random variable, but with jumps. So that is possible. There is like definitely families of random variables like that. But for this half of the course, we're mostly focusing on this example over here when we have our CDF as being differentiable. So, properties of a continuous random variable. Our CDF still looks like f of x. We also have something called a probability density function. So this is new, and it is abbreviated PDF for short. Its relationship with the CDF is that it is the derivative of the CDF. This is in contrast to the PMF we talked about with discrete random variables. So we're no longer using PMFs. We are now switching over to PDFs. The support of a continuous random variable is the values that have a positive value for the density function. So that's a lot like what we saw with PMFs with discrete random variables. We can get the CDF from a PDF. So I've defined them in terms of their CDF, and we can start with CDFs, that's fine, but we can always get the PDF from the CDF. And we can also get it vice versa through the other direction. And then if we wanted to find a probability between two values, let's say A and B, then we can integrate the PDF, the probability density function, between those values. And we'll see examples of all of these in just a minute. Let's go over some more properties. A valid PDF, f of x, must satisfy the following restrictions. The density function must be non-negative for all values in the support. and it must integrate to 1. So if you integrate over the entire real line, it's equal to 1. Now this is a lot like our restrictions for the PMFs, or discrete random variables. You can actually go back to that day when we talked about valid PMFs, and we'll find that this looks almost the same. The big difference is instead of summing over all values of the support, we are now integrating. So we're switching the summation with the integration, but we still need that all of the values for this density function, and for them, for discrete random variables was a probability mass function, we still need that to be non-negative. A couple of things we want to note. The PMF, when we talked about discrete random variables, always gave a probability. So if P of X was our PMF, then that value for P of X would just equal to the probability that X equals X. That was really handy for us from before, but that is no longer the case with PDFs. PDFs instead give a relative probability. So you can't put a value in X inside f of X, and it will not equal, or it won't necessarily equal, the probability that X is equal to X. So for example, I have a plot over here. This is an example of a PDF we might expect for continuous random variables. We have the support over here on the x-axis, and then we have the PDF plotted on the y-axis. It's this function here. Now, when I say relative probability as opposed to just a regular probability, what I mean by that is you can pick some value in the support of x, let's say it's a, and find that value on the PDF. And then we can pick another value, maybe let's say it's b, or let's actually make it a little more obvious. B over here, and have a different value. The PDF tells us that B is more likely than A because there's more mass over here, or more density over here. It's a higher point along this curve, but it doesn't necessarily tell us that exact probability. So that's what I mean by relative probability. The other thing is that the probability that X is equal to one particular value, a very specific value, is 0 for all values in the support for continuous random variable. So you could think about that as like taking an integral from a between a plus negative epsilon and a plus positive epsilon, and making epsilon super, 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 super tiny. That integral is going to become 0 as epsilon goes to 0. If you have like a very specific particular value of a, when we have these continuous random variables, that the probability of getting that exact value is 0 because we have uncountably infinite amount of possible values with the nature of continuous random variables. So that's an interesting property that's new to us that we did not have before. Some other facts we're going to talk about. Because of this property that we just mentioned, we know that the probability that X is in between any two numbers A and B is the same as it is in between those numbers inclusive. So with the equality, or maybe one's inclusive and one is not, or the other is inclusive and the other is not. All of these probabilities are the same because of that property. So we don't have to be quite as careful about equalities now. We still have the concept of an expected value as well. So the expected value of X is just equal to the integral for all the real numbers of X times its PDF. And we also have the lotus function. Again, this looks just like we had with PMFs, but we're switching out summations for integrals.